Let me introduce our speaker today. So today we have Dr. Sayantan Majumdar, and he likes to be called Monty. Yep. And he's assistant research professor of hydrologic sciences and remote sensing at the DSET Research Institute in Reno, Nevada. Oops, sorry. And he will tell us much better what he does and what he's done and all his studies, which I find really, really interesting and really nice because we share a lot of interests. But he was a postdoctoral fellow at the Department of Civil and Environmental Engineering in Colorado State University. He also had an internship at Meta or Facebook and at Planet Labs. And he's got plenty of experience in geospatial data science, machine learning, remote sensing, and scientific computing. So, which is, I find really cool. So, Dr. Montreal, thanks for being here. Yeah, there you go.
Yeah, thanks for the introduction, Juan. And yeah, I'm really excited to be here, and thanks for all of you to come here. So this is my first time in Australia, and great thanks to Pankaj for introducing me to the IH folks. So this talk, it's mostly about what I've been doing over the past 6 years or so, doing my PhD and also right now as a faculty at IRRI, and looking at how we can integrate satellite remote sensing and different hydroclimate datasets that are available, different spatial and temporal resolutions into a machine learning framework, and then quantify irrigation water use or agricultural water consumption at field to regional scales. And so these are some images. This is from a platform called OpenET. I'll talk about a bit later. And probably in Australia, you are very familiar with center pivot irrigation systems. But if there's one audience from India. So if you're from India, these are like gigantic fields. Like we mostly have small scale farm. So it was pretty neat to see these fields up close. Okay, with that, just some little bit of about me. So yeah, right now I'm at IRRI. I'm also an adjunct faculty at University of Nevada in Reno. And some of my hobbies include mountain biking, and also I'm learning guitar these days. So this is this is called Lake Tahoe. It's a real nice place near Reno, Nevada. And I'm also a scientific advisor to two startups incubated at Stanford and IIT Tirupati. Okay, so yeah, my background is very interdisciplinary, and during my before my current role, I was a postdoc at Colorado State, and also interned at Meta and Planet Labs, and before that, I was doing computer science. So from computer science, I switched to geoinformatics, and then I learned about hydrology, and now I call myself more of a hydrologist than a computer scientist. So so these are I did my PhD in Missouri, Missouri Science and Tech, and also my master's from ITC University Twente in Netherlands. So this is the outline of the talk. I'll just introduce a little bit of remote sensing and climate data, the applications of machine learning, earth science, a little bit of introduction of what's happening these days, and then come directly to the irrigation water use terminologies, different systems, and their efficiencies, and then summarizing the last 5 years of my research, how we can extend this data and methods globally, and then I'll try to answer some of the big questions that are still out there. Finally, end with the acknowledgements. So yeah, you have all probably heard about remote sensing. So with remote sensing, we can monitor large-scale areas at different spatial and temporal resolutions. And also, since I'm focusing on hydrology, I'll be talking about some of the sensors that are used in the hydrologic domain. So these are some of the sensor data and the derived products. So OpenET right on the top, that's derived from Landsat as of now. HydroSat, that's a new thermal satellite that just went up earlier this year. And then you have other sensors from Moody's, GPM, and some of the proprietary ones from Planet Labs and Max also. And obviously ISRO, the Indian Space Research Agency, and Coordination and the French Space Organization. So there are multitude of satellites available. I mostly focus on the public, the ones that are available publicly, and most of my research is on open science and data. Regarding climate data, we also have many data sets that are produced operationally at the global scale, and also for some of the North America specific data sets. And for Australia also, I think CSIRO already has some of the products that generate evapotranspiration reference, ET actuality, and so on. And so in my research as of now, I'm mostly using GridMet. So this covers entire contaminants United States, the lower 48 states, and also Prism, that's another data set that's out there. And with these data sets, these basically give us high spatial, like 1 kilometer or more, and like higher temporal resolution. So it can be hourly, daily, or monthly, which is very much needed for this kind of modeling. And these are mostly driven from data science or physical models that simulate various processes. And obviously, this is the big hot topic these days, machine learning, it's everywhere. So I'll just skip this slide, and it's just a branch of AI and computer science. And in my research, I use it as a tool. I'm not a machine learning researcher. So I use existing whatever other people develop in the computer science field. I just apply it to my research. So this was one interesting research I did at while I was interning at Facebook or Meta, looking at crop canopy height globally. And then we published this early last year. And this is one of the animations from the awesome community catalog. So if you ever want to see different data sets out there, it's a great resource along with the Earth Engine catalog. And this is a neat application of machine learning, looking at canopy height maps, which is needed for a variety of downstream applications for many stakeholders. This was one research I wasn't involved in, but this looked at groundwater dependent ecosystems using a random forest model. A couple of my collaborators, colleagues at DRI, they are involved in this research. So again, a neat application of machine learning using different publicly available data sets and producing maps that are very much needed to understand different climate and anthropogenic effects that are affecting the groundwater dependent ecosystems. And another application of machine learning. So this study, I was involved as a co-author a couple of years back, looking at, if you have heard about interferometric synthetic aperture radar, INSAR. So with INSAR, we can basically map deformation at very high precision, but doing it at scale, like at the global scale or even national scale, it's very challenging. And so the idea was like whether we can use a simple like random forest model and try to get at ground pumping induced deformation at the global scale. And this was some of the land subsidence rates classified between less than 1 centimeter per year, 1,500 and 5 centimeters. And that's a probability map coming from random forest model. So another cool application of machine learning in hydrogeology and hydrology. So now coming directly to the terminologies of my main talk. So I'll be using some of these keywords. So first of all, it's like water. So it's like as name sounds, it's like the water that's pumped to irrigation fields. And this can be sourced from both groundwater or surface water. And then you have groundwater withdrawals, which is obviously as the name suggests, it's groundwater extracted from pumped through agricultural wells. Another term in the literature that you might frequently encounter is consumptive use. So this refers to the actual amount of water that the crops used, and that's basically lost from the system. So this is very important because to know how much, like what's the water availability in a particular basin. And irrigation water requirements. So this term is coming from the Food and Agriculture Organization FAO 56 manual, which is basically the potential crop evapotranspiration that shows the theoretical demand or the maximum like water that the crop can consume under well-watered and stress-free conditions, or how much water you how much maximum water you need to apply. So with this in mind, I'll directly jump on to groundwater and irrigation systems. So usually in the US, we mostly have centrifuges and also flood irrigation going on. And these are two photos from there. So on the top, I clicked that photo in Desert Valley, Nevada, a giant centrifugal irrigation system. And then on the bottom is the US Geological Survey, flood irrigation in the Mississippi irrigating rice fields, and on top it's irrigating alfalfa field. And different systems have different efficiencies, and irrigation efficiencies are vital to knowing what's the total applied water, or if it's if you are interested in groundwater consumption, what's the total groundwater that's being applied? Because uh, uh, because efficiency, like basically that relates to the total water use. And as you know, like groundwater is obviously the largest source of hot liquid fresh water. And so many people live off heavily stressed aquifers, and it's a very precious resource that's getting exploited globally due to irrigation, but also other like drinking water, and also for data centers these days. So data centers consume a lot of water, and that's why a lot of the big tech companies like Meta, Google, they are heavily into dealing with water managers. And so one fun fact is that when I was interning at Meta, I encountered a lady who was a water manager. And so I asked her, like, what's a water manager doing at Meta? Then she described me all the nuances of data centers, and I was pretty amazed. So if you're a civil engineer or ground hydrologist and you want a career in big tech, it's out there these days. So in my PhD and even before that, like I said, my background is in computer science, and I was sitting mostly in front of a computer doing coding. And so a couple of years back, my colleagues at DRI, they took me out on the field in the middle of a desert. And I saw this sort of three different kind of wells. So one was this abundant well. We tried to look how much water level was there, but it was blocked off. But we did encounter a black-footed spider, and that was my first time after seeing the Discovery Channel, like since a kid. It's my first time encountering a black-footed spider. This was a livestock well driven by windmill, so which was also cool to see. And then the third one over here. So that was pretty fascinating, simply because, like in the Western US, like in Nevada and also most parts of the Western US, because it's kind of a desert, they'll apply a lot of water, and this kind of like alfalfa irrigation, it goes on 24/7 until the alfalfa is harvested. And then again, like once harvested, they'll again regrow it, like irrigate it, and again. So there are like 3 cutting seasons in alfalfa. And what do they do? Why do they irrigate so much alfalfa? It's because it's a very drought-resistant crop, and also it has a lot of economical value. So they'll harvest it, and then they'll sell it off to somewhere in the Middle East, where they'll feed the cattle, and then the cattle comes back again to the States. So you can see the amount of water and also carbon footprint that's involved in this process. But yeah, like I said, it has a lot of economic complexity, so we are not going into why they don't switch to other crops. Okay, so yep. And these are all mentors and colleagues at DRI who meet off this field. So with remote sensing, what do we actually see? So this is in a desert, like I said. So you get a nice contrast between irrigated lands. So these are all irrigated fields, and then the brown desert. And so with remote sensing, we always see this. If it's an RGB image, red, green, blue band. If it's more like thermal band, then use or an NIR band, you will get more information out of it. So using this combination of bands and also applying some modeling, we can figure out how much water is being consumed. So this is zoomed into Winnemucca, which is in north central Nevada, and it's in Desert Valley, which irrigates a lot of alfalfa. So one question that came to mind just by seeing those fields is how big is a pivot? So usually it's 800 meters or half a mile, which is the typical size in this Diamond Valley, one of the regions I focused on. So, and there are like hundreds of this in the middle of nowhere. So you can just guess how much water is being applied. And then we tried comparing the size of field with the University of Nevada, Las Vegas campus. It's like around 400 acres. Yeah, I don't know the exact how many square kilometers, but it's a fairly big campus. And just one over here on the left, so that's a university campus, and on the right it's golf course in Vegas. So just one center pivot was enough to cover the entire golf course, whereas 3 center pivots were enough to cover the entire campus. And then in Vegas, the golf courses are usually irrigated using reclaimed water. So it's not that they're pumping groundwater for that. But the actual elephant in the room is this irrigated fields. It's like pumping so much water, and yeah, that water just basically gets consumed for cattle feed. So if you look in the literature, there are basically three kind of broad like methodologies to estimate irrigation water use. So one is obviously through process-based models, numerical models, ModFlow. There's a farm package that helps you get an estimate of pumping, and then again that those estimated pumping values are used in the model to know groundwater availability. Other than that, there are deterministic methods. So this simplifies the process, which is like instead of running a full numerical model for getting into groundwater pumping, you get some estimates of groundwater pumping, and that might help the model. And then that model relies on crop coefficient approaches, which is based on lookup tables through the FAO manual, the FAO 56 manual, and also potential cropity and effective precipitation. This effective precipitation is basically the amount of precipitation that resides in the crop root zone after accounting for deep percolation and runoff and irrigation efficiencies. However, over the past, I would say 7 years or so, there's been a lot of push due to the computational capabilities that we have these days, and also due to the so much data availability. Like these days, people have been focusing on data-driven approaches, either using machine learning or other simple statistical methods. And during my PhD, basically, I was involved in doing such research and produced this a few papers that I'll discuss over the next slides. So these were some of the works that I did over the past 5 years or so, looking at groundwater withdrawals, how we can model it better using machine learning across different parts of the United States. Starting with this paper in 2020, which looked in the High Plains Aquifer in Kansas. So that was another heavily depleting basin in the Midwestern United States. And yes, over the years, we have improved these methods. Last year, we also looked at field scale groundwater pumping instead of looking at more regional scales. And I'll talk about that in a while. So when it comes to regional scale groundwater withdrawals, the most of the challenge that we have with remote sensing is that these are actually proxies. So for example, NDVI, the normalized difference vegetation index, that's not giving you the groundwater pumping. It's like a proxy, right? And so you need to like feature engineer your raters or in the model in a way that it can capture those correlations, like how a higher NDVI might represent more irrigation that's going on. And relating this to groundwater withdrawals using physical models can be challenging because of so many different kinds of spatial and temporal resolutions are available. And it's also difficult to estimate recharge. So if you are going into full water balance, figuring out different components of the water balance can be very challenging. And you need a lot of other ancillary information to solve a water balance. So this is an example in Kansas, my first paper for my PhD. And it's always great to see like it worked really well and got cited a lot. So this was just an example in 2014. So on the top, you have the actual groundwater withdrawals, where each pixel basically shows the total amount of pumping recorded by the flow meters in Kansas. And on the bottom, we have the predicted pumpings using the random forest model at 5 kilometer spatial resolution. And you see, like spatially, like we have a good match. And also, like if you look at the statistics in this slide, like the time series, and it's matched quite well for the most part. And it's also comparing well with the GRACE total water storage change. Interestingly, though, like if you see from 2015 onward, there's been a decline in the actual pumping, which is the blue line, which our model can't really pick up. And the reason is because our model was not trained on any management data. So it's more on, it had land use, but that's it. And then remote other like remote sensing data and also hydroclimate data, but no specific management data was used in the model. Then in a few years later, I also worked in looking at the same thing in Arizona, but in Arizona, we have a lot of subsidence going on in the state. And so this was kind of the first study that looked at how groundwater withdrawals compare against subsidence and also gap filling the entire the regions outside this model. So this is the active management areas and the irrigation non-extension areas. These are all in polygons. Outside these regions, the Arizona Department of Water Resources, they don't have flow meters installed. So they know the location of the pumping wells, but they don't have any records. And so this study basically told them like outside these basins how much like groundwater withdrawals is happening, and also compare that with land subsidence. And in this one, we sort of calculate the fraction of withdrawals that results in aqueous storage loss. And so we find like in some basins like Wilcox, which is heavily depleting, like the fraction is quite high. And overall, we see that there's a good, like for example, in Wilcox, a lot of pumping is being predicted by our model, and that's accompanied also by subsidence that the state water agency developed using INSAR approaches. And then I also looked at the Mississippi alluvial plain, looking at crop specific water use. So now we are going from more regional scale to more like crop specific, like how much does each crop, like how much groundwater withdrawals were required for each crop. And one interesting thing we found that was that this figure on this map on the bottom, like this is a coefficient of variation map. And we found that in this northwestern region, a lot of rice is irrigated and it's usually not rotated. So if it's rice field throughout this temporal period, like domain from 2014 to 2020, like it was all rice field throughout that period. But for other crops, like for example, soybeans and corn, cotton, the farmers usually rotate the crops. And that's why in regions where where rice is not grown, we see a higher coefficient of variation simply because there is high variability in the water use. And then this was, I'll present this on as a poster on day after tomorrow at IGARS. So this is looking at monthly crop specific groundwater withdrawals in this same basin. And we find that aquaculture, which is like fish culture, so that takes up a lot of water during the early growing season. But whereas as the growing season progresses, it's more rice and soybeans in this region. So now when we move from regional scale to field scale, there are some other additional like a lot of additional challenges that are present. So the first of it is matching points of diversion or wells to the places of use field. So there's no direct like database available that tells us where the water went. And so figuring that out can be very complicated because we need to look into old reports and also like discuss these things with the state a lot. Although they have some GIS data available, but it's still very challenging. And then identifying the water source type. So if you want to look at combined groundwater surface water, then it's all good. But then if you're trying to look at groundwater withdrawal specifically, you need to know which fields are irrigated by surface water or which fields use groundwater or both. And so having that information is critical. And then the other challenge is obviously field scale means we need fields. So creating and maintaining field boundaries to time, it's very challenging. Even in the US or other places like in Australia, where you have big scale farming, large scale farming going on, it's still challenging. And you can imagine the challenge in some other parts of the world, like Southeast Asia or India, where we have small scale farming. And then the other challenge is flow meter is not the only answer. So if you think just installing flow meters and recording the water use is good enough, that's not enough because the flow meters can get faulty. And there can be other discrepancies. Sometimes it's very like the farmers might fail, but will sabotage that. That happens a lot. And there's a nice book out there on this. I think it got published last year somewhere. So it's pretty fascinating to see what all happens with what you're actually thinking as validation data. Might not be actually like you may need to revalidate what you're actually thinking of as validation data. And so a lot of other challenges are there in field scale. So as part of the OpenID project, DRI is one of the members of the consortium, and I'm a member of this OpenID project, which is, as the name says, open evapotranspiration. So it uses Landsat data and the Google Earth Engine platform and provides daily to monthly scale data, actual evapotranspiration data throughout. Right now, it's available till east of the Mississippi River, but it's going CONUS wide pretty soon from 1985 to 2084. So long time period. And as part of this OpenID project, we have developed state-specific like field boundary database and attributed that with irrigation status, whether that is irrigated or not, and also look at the crop type and so on. So it's a monumental effort that has been put forward by this consortium over the past decade, which is what I'm using for downstream modeling applications. So yeah, I was talking about Diamond Valley at first. So in this paper that got published last year, so we looked at Diamond Valley and also another basin in Oregon, which is in like over here in the Northwest. It's part of the Pacific Northwest. And both these basins are semi-arid to arid in nature, and they heavily rely on groundwater for irrigation, and they mostly irrigate alfalfa. So these basins are basically a lot of groundwater depletion have been reported over the past several years, and that's why the focus was on these two basins at first. So the primary data sets that we're using here is obviously coming from OpenET, the actual ET data set. We also use precipitation from GridMet, and we also use this model called ET demands, which gives us effective precipitation. So how much precipitation is residing in the crop root zone after accounting for deep population runoff. And then we apply this simple water balance over here to get the consumptive use of the net ET. So this is the actual amount of water that was used by the crops. So when you divide that by the irrigation efficiency, you get the total water that was pumped. So this is an example showing the pairing of wells, fields, and the water rights. So which so this rectangular boxes, these are the places of use or coming from the water rights data. And then we intersect that with the fields, and then we try to do a one-to-one mapping. And also in some cases, we try to solve the many-to-one. But for the many-to-many mapping, so many-to-many means if multiple wells are irrigating multiple fields, it's very difficult to figure out where the water is going. Because to build a model, you basically need to account to sum up the evaporation data across these intersecting fields and then compare that with the meter data. So yeah, so this looked at one-to-one mapping. And then this slide is about why we need like the irrigated field boundaries. And as an example, we just show here how this honey basin was in 1991 versus what was now 10 years back. So you can see a lot of increase in the fields, and that means like although the irrigation rates might be the same, the volumes have gone up manifolds, and so that's why we need the field boundaries, because we need to know the volume of water that was consumed. So this slide, this is about the water source type. So in Oregon, we have this water source. So Diamond Valley is all groundwater. In Harney Basin, Oregon, it had mixed fields and also purely surface water and purely groundwater fields. And so we needed to mark which ones were groundwater only. And so these red ones are the groundwater only fields. And we took these fields for our modeling. And then, like I said, like the flow meter data itself can be very noisy. And so in this case, OpenET is fairly accurate in arid regions and semi-arid regions over irrigated fields, very low bias, and we were very confident in the OpenET data. And so that's why when we have this kind of discrepancies, like it's either happening due to faulty meters. So we take the ratio of the groundwater pumping, we put it from the flow meters over the net ET or the consumptive use that's we're calculating. And so if it's very high or very low, then we are pretty sure like it's either happening due to faulty meters or some discrepancy in the meter data, or the way we are joining the fields and the wells. So the model of the study here is metering is not as trivial as it sounds. So looking at the results, we found that so x-axis we have the net. This is our model predictor, and in this simple linear regression, we try to predict the groundwater pumping, and we find that the R square is around close to 0.7 for Diamond Valley, and for Harney Basin it's around 0.5. And this is for the test data. So we split the data in 70 and 30% randomly. And then this slope basically gives us the idea about irrigation efficiency, simply because, like I said, net ET over GP, that's the irrigation efficiency factor. This is looking at the same thing at the volume scale. So the volume space, you'll notice that although the R square in the weight space, or like in millimeter space, it was like 0.66. The R square over here went up to 0.93. And the reason is because you're regressing over irrigated field boundaries, and it's trying to impose an artificial correlation where the bigger the field, the more water it will consume. And so that's why that artificial correlation is imposed. So when you're trying to do this kind of modeling, you should always model at the depth space or the rate space and not the volume space. Because otherwise, if you just have the irrigated field boundaries and no other parameters, like you don't include precipitation, ET, nothing, then also you'll get an R square of 0.7 or 0.8. But that doesn't make sense because the whole purpose of this is to know what's the water consumption going to be in the, let's say, next 4 or 5 years. And then you don't know how the field boundaries are going to be changed over that time. But we do have ideas from climate models and other models that how the temperature is going up and or in some cases going down. So yeah, so we should always model this at the depth space. And then we compared this at the basin scale also, and we found that overall the Nevada Division of Water Resources report in the Diamond Valley, now our estimates were around 7% of the report. In Harmony Basin, it was a bit worse from the Oregon Water Resources Department. It was around 17%. And this red line over here in Diamond Valley, so that's what the state used before, which like assuming like it was 3 feet of, like close to 3 feet. I'm sorry, excuse me if I'm using the wrong units, but yeah, that's it's like 100, close to 100 megameter cube. So that line basically represents like what the state assumed before we sort of showed this model, which is very much overestimating the pumping. Yeah, this kind of modeling actually helped the state understand like it's not the same throughout the basin for all years. And so NATD over GP, the same thing, like it gives you the irrigation efficiency. And in Diamond Valley, we found that it was around 90%. In Harney Basin, it was around 83%. It was a bit lower because Harney Basin also uses flood irrigations, whereas Diamond Valley is mostly using the LIPA system, which is the low elevation precision application. So it goes almost to the canopy and almost in some cases also below canopy. So it's a very highly efficient system. And that so our findings basically corroborate with whatever the farmers and the state basically reported in terms of the irrigation, which was nice to see because if you think broadly, we are trying to do this modeling from space. So it's a lot of issues are there. And then this plot basically shows how the net ET or the consumptive use and the ground pumping compared in Diamond Valley. I got 6 or 7 ensemble models that are out there. And so this black line is from the open ensemble and it compares pretty well with the ground pumping. And this difference is because of the irrigation efficiency. And you can see this lining up pretty well with the blue dashed line, which is the ground pumping. And this was aired, like my colleague Thomas over here. This was aired in a news channel, which is pretty nice to see. So ultimately, what we are trying to do, so we are trying to build this database as part of the Nevada Water Initiative project, agricultural water use and pumping inventory. So looking at developing well-specific database, field-specific database, and basin-specific database of irrigation consumption, like consumptive use, applied water rates, and then tying that with also the volumes, obviously. And then also the annual classifications of irrigation, the per field efficiencies, and the crop type. So it's a monumental effort. I'm just only playing a small role in that effort. An interesting finding that I presented just today morning was that in Diamond Valley, we compared this pumping from the OpenET project or the Nevada Water Initiative project, and then try to compare that with the groundwater levels in the region. And also compare that with INSAR-derived land deformation. So this is the mean deformation that's happening between 2014 and 2021. 2014 and 2024. And we found that the deformation rates is around like more than 50 millimeters per year in some regions, particularly in the Central Valley. And that followed pretty much patterns of the ground level declines. And the reason that happened is because between 1985 and 2020, this one shows the rate space, but if you look at the volumes, it nearly doubled in that time. So a lot of pumping is happening. So as part of this project that I have with NASA, we are also looking at improving the model that I showed for Arizona with some of the latest data sets that are out there, mostly available from the Google Earth Engine catalog and also the awesome GE community catalog. So yeah, a lot of big data analysis and modeling went in, and we found that for this particular basin, so the model is doing quite well. Whereas, so this is in Phoenix, for example, Phoenix active management area, where we, so this blue shaded line is basically where we don't train the model with any data. So it's like a test period. The model doesn't see this data from 2014 to 2024 to 2023. I have recently updated that with till 2024 also. Similarly, in this Tucson active management area, also we see good fit at the basin scale. This one, although visually it looks very bad, particularly for the later years, but this one was an interesting result because this entire basin was held out from the model. So the model never saw this basin. And even though like machine learning models have been known to do not very good when you hold out entire regions, so it still picked up some of the pumping quite well in the early years. Between 2000, I would say 11 onward, there have been a lot of management decisions that have been taking place in this particular basin. As an example, in 2011, the state diverted a lot of water from the pumping wells for municipal use. So the model obviously doesn't know that because we are only using the irrigation wells in this case. And so if water is diverted for municipal purposes while it was taken from irrigation wells, the model has no idea of that. And so that huge spike is basically getting missed by the model. But overall, across all the active management areas and the irrigation non-expansion areas, we are seeing good model fit. The R-square is pretty nice. And also the RMSE and MAE and the mean bias percentage is not that bad. And we also tried looking at holding out different sets of years. So training the model with a few years and then leaving out certain years. And this gives us test R-square around 0.71. And the model is not overfitting by that much. Similarly, in this one, we just held out randomly 2007 and just tried to see what the model is doing. And so in this case, the R-square kind of improved, although the mean bias error is kind of high. So to finally summarize, and I think I'm just on the nick of time, the current techniques that are getting used for round of withdrawals are either time consuming. Like if you use a numerical model, obviously it will take a lot of time and you need to put a lot of time in calibrating the model. With statistical approaches and data-driven approaches, like it's basically bypasses that kind of extensive calibration that you need. And we find that it basically can explain 50% to 80% of the variance in pumping depths and 90% in volumes. And out of all the 6 or like the 7 models in the OpenAI ensemble or the OpenAI product, so the OpenAI product has like 7 models, including the ensemble. So we find that the ensemble mean produces the most consistent and accurate results. And obviously, like our data-driven approach is more systematic. We are not assuming anything like the state did. So yeah, overall, we are pretty much advancing the state of the art in this field. These are some slides I put just to if you are interested in doing this in Australia or some other place. So how do we extend this data and methods to other parts of the world? So if you know in the remote, if you've heard of this Trishna mission that's coming out from the Indian Space Research Organization and the French Space Agency. So this is looking at primarily meant for irrigation water use. Like that's written on their main portal if you go there. But the whole reason I put this over here is that having new satellites is great, but that's not the only thing you need. So because like I said, field boundaries, like you're doing at field scale and you want to do field scale management, you need field boundaries without which you can't do anything. So fields of the world, if you just look it up, it's a really great AI-based product that's out there, openly available. In most cases, it's very hard to do things manually. But combination of, I would say, manual labor plus AI is probably the way forward. You can't do simply anything like not everything with AI. And as an example, this is a great example. So this study was, I think, published in 2021 or 22, looking at small scale farming in Cambodia and Vietnam. And they compare different model outputs. So this one is from Sentinel-2, And last one is from Google Maps, that uses high resolution max RGB. And these are great. Like these are generated using AI, like some method called unit, which gives you segmented field boundaries. All great. You read the paper, they talk about reference boundaries. So anyone in this room has any idea like how do they develop those reference boundaries? So if you read the paper, they'll say like we hired a bunch of, they don't say bunch of, we hired a lot of photogrammetry experts and image analysts, and then they develop this manually digitize all these fields. So that's how does the reference boundary for the CI model. So the whole idea is if you are trying to do this thing, you can't just rely on AI. You need some reference boundary, and that reference boundary even can be very difficult to get access in some parts of the world. So obviously the solution is to go into multi-agency collaborations. Australia is obviously, it has good collaborations. But this slide was mostly meant for some of the other developing nations that are out there. And so if you are trying to do this in Australia, I put this screenshot in the bottom from Google Earth Engine. So CSIR has a great actually water transmission data that's operationally produced. And with this, you can, and it's also great from Lens. So with this, you can pretty much apply whatever I talked about. Any models, it can be easily transferred to Australia. Other than that, OpenAD was recently expanded to the Amazon basin. Brazil is running, has already run 3 of the OpenAD models. And pretty soon, like by 2028, they're going to have the OpenAD Brazil fully working. And we're also expanding to some other parts of the world as well. So yeah, I would like to conclude by thanking all my colleagues and collaborators and mentors, without whom I won't be here today in Australia. And pretty much I wouldn't have done my PhD as well. So yeah, great thanks to them, all my collaborators, and you'll see Pankaj is added there from WSP, but next time I talk about this, I'll include CSIR over there. So yeah, and these are the agencies that supported my work. These are some of the references, and I'll just end this with the picture of this koala that I took in the Lone Pine Sanctuary a few days back last week. And like this koala is holding on the branch. I'll be defending on the questions that is throughout. So yeah, great to be here. Let's follow.
Thanks a lot, Sayantan. So yeah, there was a whole lot of information to go through. I can see, but let's see, has anyone got questions? Let's go with questions in the room, and I'll check if we've got any questions online as well. But in the room, do we have any questions?
And you don't have to start. The example Kansas. You know, it's almost entirely groundwater destruction.
Yeah,
What are the cases where you have to
yeah, so in places, so first I'll answer the question about Kansas. Kansas, whatever the map that you saw over there, see again. Here. This one, yeah. Yeah, so Kansas, it's the only state in the US that has almost 95% monitoring of their wells for pumping. So they have extensive, and they do a great job at monitoring and maintaining quality of the well. So from that database, we basically pick the ground of pumping records. So these are all ground of pumping. And so each 5 kilometer pixel over here, it shows the cumulative pumping that's happening from that area. So yeah, so this is all ground. Yeah, we are sure about that.
Yeah, so sorry, I used the wrong thing.
Yeah.
In a case that.
Yeah, in Oregon, for example, where we have mixed, and we're trying to develop that database, and also in Nevada, also we have mixed fields. So far the solution that we have come, like previously what the USGS was doing, and we were also kind of following, was just assuming it's 50-50. Wherever it's mixed. But right now we are trying to be a bit clever and sort of introduce SPI, which is standardized precipitation over transmission index, and also looking at SPI also, standardized precipitation index, which are basically drought indicators. So if it's a mixed field and if it's drought season, if the SPI is negative, they are like below like around 2 or 1.5 or something, negative 1.5 something, then we are trying to do that, like kind of develop a scale between -1 and +1, sorry, between 0 and 1, and that sort of acts as a fraction, like how much we are multiplying. So if it's a drought year, we'll multiply the groundwater used by more fraction. Let's say 0.7 instead of. But there's no validation for that. It's all assumption. There's no validation. So yeah, we have. I don't have the slides here, but as part of the Nevada Water Institute project, we have applied that scaling factor, trying to see how it compares up to basin scale where we have inputs.
I've got a question. When you mention subsidence and calculating pumping from subsidence data sets, like the data sets that you use, did you have to do any pre-processing or cleaning, or are they like ready to use? And is the data in good shape? And also, that's question 1. And question 2 is, did you find any problems with the accuracy of subsidence? Like if subsidence is just a little bit, does it still work well, or is there a point where you say, no, this is just noise and it doesn't work almost?
So in Arizona, we didn't process subsidence data ourselves. We got it from the Arizona Department of Water Resources when they already have an operational program. They use the Sentinel-1 platform and they process their own subsidence data. So we took that data and then compared with the ground visuals. That's that. And all fairly, they are like confident that but it's quite good, and they have some publications also from there. I don't have like the current number off the top of my head, like how much accurate the subsidence, but they are actually monitored. They have sensors, GPS centers, sensors throughout the state, and they monitor that. In terms of Diamond Valley, the one I processed, so I got the data from the Alaska site facility. So they have today morning also, like when I was presenting about that. When I started working on INSAR in 2018, just processing one or two interpreters would take me like 8 hours compute time. Due to the time it takes for the phase and part of the INSAR workflow. You won't believe if I say like 843 interpreters, like a whole time series that I used to get that deformation map. So I didn't just use a pair of interpreters between 2014 and 2024. I used a series. It's called a method called SBAS. Which basically reduces the noise in that stack of everything. So that was developed back in 2002. So it's fairly common to use these days. So Alaska site facility using that, their portal and it's freely available. I was able to process 843 interprograms in 40 minutes. So in 2018, from 8 hours to process 2 interprograms to 40 minutes, 843 interprograms, depending on the power that we have. And it's all open. They don't use an open access open source software. There's a proprietary software called Gamma SAR, but they have the platform to do that, and anyone can access that for free. So with that, the next step is to compare that with GPS records that are available. There are no GPS systems within that Diamond Valley basin, but there are some that are there outside. So we can do that comparison. But as a pseudo sort of validation, we sort of try to compare the deformation rates with the groundwater levels at co-located pixels, co-located locations also. So I don't show that slide here, but I do have this talk about this. So at co-located pixels, how much and co-located monitoring sites, how much the deformation rate is and how much the groundwater level declines. You see a really good match between those two. So that's how we sort of validate it. Now also try to find out the reasoning. We compared that with the OpenET guide compilation. Find that obviously if you're doubling your pumping in a period of 40 years, and then it's all clay as clays out, like because the prehistoric clay, so it has thick clays there, so it's compact. But yeah, we need to do a proper validation, but that's a little difficult if you want to do that. It is a proper program on itself, like we actually use. I hope that was a good answer.
Do you take into account like energy resistance within the air you remove that information?
Yeah, so we only picked sites that had croplands. And for Kansas, though, since we picked a 5 kilometer grid, we also included urban areas, urban lands from a land use land cover map. It's called the USDA cropland data layer, which is like available freely throughout the entire 48 states from 2008 on at 30-meter resolution. So we use that land use land cover map to filter out other non-agriculture and non-urban use. That's how we know that. Yes. For the other studies, like in Addison also we did the same thing. For Diamond Valley, we just have a field boundary, so we know it's all irrigation.
All right. I'm not sure anyone joined online. What I'm not sure if the online presentation worked, but at least we've got a recording.